Phase control rectifiers. Rectifier is a device which converts AC supply into DC supply. The diode rectifier provides a fixed output voltage only. To obtain control output voltages, phase control thyristors are used instead of diodes. Since these rectifiers convert from AC to DC, these controlled rectifiers are also called AC to DC converters, and they are used extensively in industrial applications, especially in variable speed drives ranging from fractional horsepower to megawatt power level. The output voltage of the thyristor rectifier is varied by controlling the delay or firing angle of the thyristor. A phase control thyristor is turned on by applying a short pulse to the gate and turned off due to natural or line commutation. In case of highly inductive load, it is turned off by firing another thyristor of the rectifier during the negative half cycle of the input voltage. Advantages of the phase control thyristor. The phase control rectifiers are simple and less expensive, and the efficiency of these rectifiers is generally about 95%. Phase control rectifiers classified into two types, that is single phase rectifier as well as three phase rectifier, and each type can be subdivided into semi converter, fully converter and dual converter. The semi converter will have one quadrant operation, that is both output current and voltage are in first quadrant, whereas fully converter is known as two quadrant converter, and the polarities of output voltage can be either positive or negative, V0 plus and V0 minus. However, the output current only positive. So this is first quadrant operation, two quadrant operation. Then the dual converter will have four quadrant operation. Both the currents and voltages, that is I0, will have two polarities, I0 plus, I0 minus. Similarly, V0 plus, V0 minus. So this will give a four quadrant operation, V0, I0, minus V0, minus I0. Let us consider a single phase thyristor converter with resistive load. This is the circuit for the single phase thyristor converter. The Vp is the input given to the transformer primary, and the Vs is the Vm sin omega t, that is input voltage. As soon as the input is given to the thyristor anode is having the higher potential than the cathode. Then the thyristor goes on to the forward biased. Then the voltage across the Vt is going to rise. If the thyristor turns on, then only load is going to receive the power from the input. But to turn on the thyristor, we need to wait until this Vt voltage rises to breakdown voltage, which is not desirable. Then we'll turn on this thyristor by simply using a pulse between the gate and cathode, and this pulse is given to turn on the thyristor. The time after the input voltage starts to go positive until the thyristor is fired is called delay or firing angle. When the thyristor T1 is fired at omega t equals to alpha, then T1 conducts and the input voltage is going to appear at the output. And this is going to conduct until the thyristor is in forward biased. At omega t equals to pi, the input voltage will become a negative. So here the negative voltage and here the positive voltage. At this instant, anode will become a lower potential than the cathode. The thyristor will be in reverse biased, where the thyristor stops conducting and the output voltage will remain 0. When the thyristor stops conducting, that voltage is going to appear across the thyristor Vt, whereas this is the output voltage appears across the load. This is our V0. Then the current across the load will be present when the voltage is going to present across the load, and that is given by I0 equals to V0 divided by R. By simply varying alpha from 0 to pi, we can vary the output voltage across the load. That is why this is called a controlled rectifier. This converter is not normally used in industrial applications because its output has the high ripple content and low ripple frequency. Input voltage Vs equals to Vm sine omega t. Then the output voltage, that is DC voltage VDC, is given by the total length, that is 1 by 2 pi integral of this pulse is going to start at alpha, so alpha, and ends at pi, so pi Vm sine omega t d omega t. Vm is the constant divided by 2 pi. When you integrate the sine, you are going to get minus cos omega t, and the omega t value varies between alpha to pi. Vm by 2 pi of 1 plus cos alpha. These are DC voltage or the average output voltage. VDC maximum at cos alpha equals to 1, which is nothing but alpha equals to 0 degrees. VDC max value will be Vm by 2 pi, 1 plus 1, nothing but 2, so this will be Vm by pi. VDC is minimum when cos alpha equals to minus 1 at alpha equals to pi, and VDC will be 0. This is the average output voltage of the single phase thyristor converter with R load, and this is the maximum output voltage. Let us find out the RMS output voltage. Vrms equals to 1 by 2 pi integral alpha to pi Vm square sine square omega t d omega t under the square root. This will be Vm square by 2 pi integral alpha to pi sine square omega t. We can write that in terms of cos terms, that is 1 minus cos 2 omega t divided by 2. I am taking that 2 out, so 2 into 2 is 4, 1 by 2. Now when you solve this, we are going to get Vm by 2, taking out of the square root, then 1 by pi, integrating 1, you are going to get omega t, then substituting the limits, that is pi minus alpha plus sine 2 omega t limits, that is pi by pi, which is 0, plus sine 2 alpha by 2 under the square root. Then Vrms equals to Vm by 2 1 by pi of pi minus alpha plus sine 2 alpha divided by 2 under the square root. RMS voltage of the single phase thyristor converter with R load.